Full screen. All right. Sometime last week, I think I posted this graph. And I asked the question, how do you add these two graphs up to get a constant of 25? X squared plus y squared equals 25. How do you do it graphically? And when I posed that question to myself, I didn't have an immediate answer. And a lot of it is just because of the training, I think, that we get working with functions, that the brain has a hard time switching from that X to Y perspective. But I won't say any more than that. I'll just say that it brought to mind a lot of questions about how to get the job done. So I'm going to leave it there and come back to it later on in this video, and we'll talk about it. But you can pause the video, think about it for as long as you want. A lot of times it's great to really not get an answer quickly and have to work for it. I think you learn a lot more when you sit with a problem and really think about it for a long period of time. And then when the answer comes, it's very gratifying. So you might want to have that experience. It will also bring us to a discussion about implicit differentiation. And I think a lot of this happened because Yasser said he was going to look back in his textbooks at that topic and reacquaint himself with it. And that got me thinking about something else as well. But let's get to the main topic in this video, which is really about differentials and whether or not we maybe can think of differentials as just synonymous with the word changes. We take some poetic license with what a differential is and use it in the context of other things that we've been studying the past couple of weeks. We're only 2 or 3 weeks into a semester, and I think we're moving at a good pace. We got a lot of good discussions in front of us, a lot of different algorithms, a lot of different functions to study. And let's take a look at where we're at with the exponential. We're looking at changes from X to Y, and let's have a go at it. So at this stage, I hope a lot of my students can simply write the equation. 3 plus 7 next time, not 7, 14. X minus 1900 over 105. And I've got students who can write that just as quickly as I just did now. With practice, a couple of minutes a day, every day, and we get there. All right, so here's our differentials. There's our first differential, 7. And the second differential is 14, and we really have some ratios of change. And that's why I'm wondering if we can use that word in the context of creating a new algorithm, a new function over here in a moment. All right, and this multiplication takes one differential and converts it into the other. All right, can we use that concept when we're looking at writing this equation? So I've got a parabola centered at 3, 2. So I could write x minus 3 squared plus 2. These markers last. And I want 8 to get me 27. So if I put 8 in, 8 minus 3, 5 squared is a jump of 25. That's my first differential. And what do I want from 2 to 27? 25. Okay, well, that works. So I have it right in front of me. But what if I wanted that parabola to go through at 60, an altitude of 60? All right, well, people who teach transformations would say the graph just stretched. Okay, yeah, I need a lot of stretching these days, but I use that mostly for my body, not for parabolas. What I'm looking at is the differential. If I go over 5 and I square it, this produces a change. And we kind of do so much mx plus b to students in algebra 1 that it's hard to get the brain out of that thought process. This is just adding one calculation to, run. X minus 3 is run, as defined by somebody some point in time. Run. Okay, well, run, I guess, means move horizontally. I don't know, but you're moving 5 units, but squaring it is the numerical change in a problem, and you got to play with numbers. So what I've created is 25 plus 2. That's what I have just created when I use the number 8 in this equation. Well, 25 plus 2 does not take me to 60. This differential of 25 units doesn't work. What does work? Okay, well, I'm looking at a ratio of change here, 2 to 60, 58 works. So I don't want that differential, that difference, that change. I wanted that change. Again, a multiplication. This gave me 25 units when I put 8 in. Cancel that change the same way I do over here in the exponential. Come on, markers, stay with me. Hope you can see that. We could use it in the square root function. Square root function. X minus 3 plus 2. Why can I say that? Well, square roots are side lengths of a square. And so 16 is, when I do the square root of 16, I'm looking at the side length if that's the area of a square. And we can see it's 4. Okay, so over here, I just put some dots on the Cartesian coordinate systems. Well, I haven't shown the whole Cartesian coordinate system, but 16 units of area gets me 4 units of side length. And 9, and I cut 16 in half so I could get a decent. I cut that in half too. I tried to. So 9 is about here. That gets me 3 units. Call them that 3, 2, 1. Just get a feel, and I get this shape. I see that shape over here. It tells me I'm looking at a square root function. Could be. And there's a smallest side to a square, 0. We don't take square roots and negatives and put those numbers on a Cartesian coordinate system. Somebody made one coming out from the wall. Okay, that's fine. So square roots start somewhere. So 0, so I want this starting somewhere, then 3 has to act like a 0. Okay, just a little bit of a conversation that we've had going now for 3 weeks. And hopefully each time we talk about it means a little bit more to you. So what do I get if I put 9 in? Well, I get a differential. Right? I get 9 minus 3 square root of 6. I get the differential, the square root of 6. Do I want that differential? Not quite sure where to show it. So I'm not gonna belabor that. But square root of 6 plus 2 certainly does not take me to 7. So what do we do with the differential? We get rid of it, and we figure out what plus 2 is 7, and that allows us to write this function quickly and easily. So you have to play with numbers to understand mathematics. So where are we going to go? Well, within 2 weeks, we haven't introduced any trig, but I'm hoping 2 weeks from now, I've had students do this in 2 or 3 days because of the work we've done already. I'm just going to write this equation. I haven't even talked about the function, what causes it, but I'd like my students to look at it and say, how much of that can I write without any work? How much do I, after I write the equation, how much can I recognize out of what I'm going to write? All right, so I look at that and I go, and I say 40 plus 10, I'm going to make it a sine function, and I'm going to take 1900, I'm going to make it a 0. We've had a lot of practice with that, and I'm going to convert that into pi over 2. And then I'm going to look at this, and I'm going to say 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi over 105. Can you look at some of those numbers and see where they might have come from and why? It'll help you to learn to think mathematically, because we're always going from how do I change that number into that number? That's what we're basically doing. Okay. Get it further up, then you add another variable, X, Y, and Z. All different level of study. So I'll just leave that there. I'm not going to talk about anything else. I'll be doing that in the next 2 weeks, starting to put some of those, maybe with the newer material, in the lesson sets. Maybe put the newer material in the front, the older material in the back. That's a good thought. But if you want to know where things come from, you got to play with numbers. Now, we haven't studied hyperbolas, and there's asymptotic behavior in hyperbola. And if you want to see the asymptotic behavior, it occurs at the end, then you got to put numbers in, like let x equal 100, solve for y, let x equal 101, solve for y, and look at the change in the table. And if you do that, I think you could change it, multiply everything by 144, and work with that a little easier in case you decide to do it. But then you might understand the asymptotic behavior of this function. All right, now back to the other side of the room. Wasn't a function, I misspoke there. Not gonna stop and do this over again because I don't have time today. But we're back to this, where we started. X squared plus y squared equals 25. And and again, you don't have to listen to this part of the discussion. You can stop right there and think about this for a longer period of time. But it came to my mind that it would have been helpful for my students in calculus when they got to volumes of revolution if they were more familiar with writing x as a function of y. So we have vertical amounts here. When x is 5, we have 25 units, a differential of 25. That satisfies it, which means that y has to be 0. I'm calculating with y. Whereas when x is 4, I got 16 units of a differential, right? I've got 16 units. Hope I can use that word in this context. And so I got to have 9 units here, which could come from 3 or -3. All right, so, well, let's put -3 in. What do we get? We get 9 units of change, but that change is not vertical change. It's not being expressed vertically. It's being expressed horizontally. And so when we put 5 in, we really get a y change of 25 units. Correspondingly, when I put -3 in, I get an x change of 9 units, which means that 4 -3 satisfies this relation. And so does 5 for x, 0 for y. All right, and this gives a little bit of practice of writing x as a function of y. And that's how you could have added these amounts up. And I think you probably can see it here with the 16 and the 9. Right? If I tack that 9 units here, then both of those work together to satisfy that equation. And so that's how you could have used, I believe that's how to visualize graphically the circular rotation. And now I'm on this topic because we've been trying to write x squared plus 6x plus y squared minus 10y equals 24. We've been trying to change those into the Pythagorean relationship based on squares. So that's what prompted this discussion. And we're going to continue with it and build off it. So the mechanics of this is what we're currently practicing in class. Y minus 5 squared minus 25 equals 24. And let's see if I've got the number that I wanted. No, I didn't get what I wanted. So 9 and 25, 34. Yeah, I guess I did 125, huh? No, I wanted 15. I've done that a couple of times now. So if these were the numbers that I had originally placed on the board, then I'd have 34 and 15, which is 49. So x plus 3 squared plus y minus 5 squared equals 49. And we can begin to see the relationship between a side length of x plus 3, y minus 5, and 7. And we'll continue having discussions centering this at -3, 5. All right, so that's where we're headed, and enough of that. All right, so let's get back to the x squared plus y squared. Oops, Rene Descartes just hit a snag, so we're on the tables now. And just a few more comments about playing with numbers, because this is when Yasha said he was going to go back and look at his implicit differentiation. It really brings up this I think highlights this ratio of change, ratio of differentials. So if you had an instant of a 3x3 and a 4x4 adding up to 25, 9, and 16, which we just talked about, what happens when it changes at an instant? Well, we've got to work with some small numbers. And if you put 0.001 in, so in a table, we have 3 and 4, and now I'm going to change that to 3.001, then how does this number here change? Well, let's see if I'm running out of ink here, what I have. Got another marker here. All right, hoping red shows up. So 3 times 0.001 means this thing went up by 0.003, which means this one has to go down by 0.003. I've got to get minus 0.003 out of this layer of change because they're adding up to be a constant. One goes up, the other's got to go down. Now, if I solve that, I get dy, this change here has to be minus 0.0075. And if I want to talk about slope, then it's the change in y over the change in x. And in that instant, let's see if I can bring Rene down here now. Yep. So if I bring that down here now, I can look at the numerics. And again, if you want to understand what's going on with calculations, I think you got to perform a calculation. So I performed this calculation. I divided the change in y divided by that change in x, how those dimensions changed. Maybe I can even think of dx as a dimensional change in x, in this case, a really small one. All right, and dy, dimensional change in y. Maybe I can use that language. Language matters. And if I do that, I move the decimal place 3 places, right? 3 places. And I get negative 0.75 over 1, which I recognize as negative 3/4. And that jumps off the board at me because I started with an x value of 3 and a y value of 4. So I guess I get very curious at this point. And I ask myself, would that change always be the case? Would it always be minus x over y? And the answer is yes, it would be. So we go and do the implicit differentiation. X squared plus y squared equals 25. We look at what we had over there. We really have a y value here, a y value here, yes. And so I've got adding up 2 strips of y times that little bit of change, 2y dy, 2x dx, but I want dy over dx. So algebraically, I divide every term by dx. That gives me dy over dx here. We just have to isolate it. Right? The dx's turn out to be a division of 1. 1 times 2x is 2x, giving me this line of work, moving the 2x to the other side, dividing by 2y, dividing out the 2's, and I get minus x over y. It kind of verifies that something going on here. And the last thing I want to talk about, since we're starting to have early forays into calculus, and I do believe planting seeds is important. Let's look at y equals x squared and y prime equals 2x. Done that enough now, I can say that. Y prime is a representation of y2 minus y1 over x2 minus x1 equals 2x over 1. And inverse operations, the inverse of y equals x squared is y squared equals x, which is y equals plus or minus the square root of x. I'm just going to look at the positive square root of x. And I can see that 3, 9 gives me 6 over 1. 9, 3 gives me actually 1 over 6. Where does that come from? Well, if you switch the x's and the y's, y2 minus y1 over x2 minus x1 gets you x2 minus x1 over y2 minus y1. The inverse of multiplication by 2 is division by 2. And switching the x's and the y's puts the y in the denominator. All right, I hope I haven't misspoken. But from a calculus standpoint, y equals the square root of x, y equals x to the 1/2 is the same thing. And taking the, the first derivative that you learn how to work with is polynomial probably. Multiplying by 1/2, dropping down by 1, gives us 1/2 root x. And what is root x? Another name for root x is y. So I'll replace square root of x with y. And that's just another aspect of implicit differentiation to look at. All right, said a mouthful here. And I hope it makes some sense. But like anything else, when you hear something for the first time, probably doesn't. But it's nice if you hear it again. That's why we're doing the lesson sets we're doing. Keep doing repetitive problems so we keep talking about them, look at them geometrically, numerically, graphically, and algebraically. All right. Talk later about this, I'm sure.